Kids, this is Mr. Pickett. I started the last video and then my kid on cue was puking, so took care of that and hopefully we're good to go. So, yeah, that's why I'm not here today. My littlest guy, Strider, he's not feeling very good, and that's okay. So I'm getting this lesson in. Um, Hopefully it won't be too quick. But as this is going, when I ask you to pause and please do that, and then continue do your activity and then continue on with the lesson. So the first thing that I want to do is I want to talk about the assignment, the modeling activity that you guys were supposed to do. And this was supposed to be kind of your final product, you guys filling this out. A lot of it was really good, but some of it concerned me a little bit because we had some students that, and I'll just kind of start filling this thing out a little bit, that filled this in correctly. They recognized that they needed to put these things in. And then I had many kids that ended up having a force that looked like this, maybe on this side too. It really doesn't matter what side it's on, but if I look at this and I read it, I have an object with a medium amount of velocity, so it's going medium speed, if you will, that encounters a force in the same direction that it's moving. This is a pull force, by the way. If it's on the other side, it's a push force, but it's already going medium speed, and then in the same direction experiences a force, and somehow that's going to cause it to slow down. I don't think that that's true. I think that if you're going in a direction and a force acts on you in the same direction that you're traveling, it's going to make you get faster. So I get why kids put that here, but I believe that you need to either put a force that's kind of a pushing force acting on the object. So object is moving and it kind of pushes it to slow it down, or you have some sort of pull force. So maybe somebody's moving and you've got like a bungee cord on them that's causing them to slow down. Either way, I think that you have to have the force that's being applied in an opposite direction of travel in order to get it to slow down, because that's what's happening here. Now, when I look at the next one, right, I have an object that is traveling a medium velocity to the right. Some force it encounters, and then it looks like it comes to a stop. And again, if I'm thinking about this, right, in order to make it come to a stop, I have to have a force that is opposing its current motion. And if a little force or small force caused it to slow down a little bit, maybe a medium force is going to cause it to come to a stop. Now, it does not matter if the force is in this case, a pull force or a push force. It matters the direction that the force is pointed in. And if the object is traveling to the right initially at the start, then I need to have my force acting in the opposite direction to cause it to slow down and eventually cause it to come to a rest. Now, we have, again, the same object that is moving with a medium velocity. It's moving to the right. It encounters some force, and then it's actually traveling in the opposite direction. It's not going very quickly. It's going slow, but it's moving in the opposite direction. And again, I think in order to do that, it's got to slow down, come to a stop, and then keep going. So I believe that the best answer is this one, right? A larger force is going to cause a greater change in its velocity. Now, again, it does not matter if it's on this side or this side. What does matter is the direction. And so many of you, I think, are really hung up on like what side of the object am I applying the force, instead of really thinking about, well, which direction is my force being applied? In this first one, it slows down. In this next one, it slows down to a stop, and it'll slow down to a stop and then get faster because there's a greater change in the velocity. So hopefully this helps you out. Don't be afraid to go back in and take a look at your thinking and see how you did. Okay, so we're going to shift gears here a little bit, and we're going to move over to lesson 1-6. So please make your way over there. And what we're going to be doing in this lesson is we're going to do a little bit more modeling. of the pod activity that we had started the unit with, and then you're going to have an opportunity to write. So make sure that you have your science notebook out, and you have your, obviously, and this is going to be tough. Like, how do you listen to me and watch this at the same time? Let me show you what you have the ability to do. It's kind of difficult, is you can, I have way too many tabs opened up here, but you can take this maybe YouTube tab, and then maybe your amplify tab, which I'll have maybe amplify over here. Yeah, actually, I'll just do this because you guys can't see anybody's name. Right. As of right now, 15 of the 18 of you have finished that modeling activity. So I have these two different kind of windows. What I'm going to do is I'm going to hold on to the green. I don't even need to hold on to it. I can hover over it, or I can click and hold. And I might hit tile window to the right, and I'll click my other window, tile it to the left. And I have the ability to work on two things at once. So if you're listening to me, which is awesome, and following along, please do so, and then maybe have your amplify opened up on a different side. Some of you will just use a 3-finger swipe and move things over, and that's okay as well. So the first thing that I want you guys to do is get to the warm-up, so tab 1, and I want you to take a look at the two things that it's going to ask you, right? So in most cases, pods move in one direction, and the thrusters exert a force in the opposite direction. The right amount of force should make a pod stop moving so it can dock. The pod is representing the puck. Hopefully everyone has gotten that right now. So in claim 1, the thrusters cause the pod to move in the opposite direction. In claim 2, the thrusters only slowed the pod. It didn't stop. The pod hit the space station, which made it bounce and move in the opposite direction. So both of these claims explain the situation that we saw, right? We saw a pod coming in, then a video cut out, and then the pod literally going off in the other direction. So both of these claims honestly have the ability to explain what we saw. So what could we infer? That inference word, or that infer word, which you guys saw in 1.5, what can we infer about the thruster force that would have caused the situation described in claim number 1? Pause and think. And then I want you to turn this back on. And what about claim number 2? Pause and think. I hope that after you think about the first situation and the second situation, you're comparing the amount of force, if that existed maybe in claim 1 and claim 2. I also think you need to be thinking about the pod coming into the right, and some force, which is the thrusters, that's moving in the opposite direction. What can we infer without knowing, right? What can we infer about the force in claim 1 as compared to the force in claim 2? I'm hoping what you'll think about is that the thrusters in claim 1, that force was larger because it caused, that force from the thrusters caused the pod to move in the opposite direction. And the thrusters in claim 2 were pretty weak, and they never got it to come to a stop. And the thing that actually caused the pod to move back wasn't the force of the thrusters, but it was the force of the collision with the space station. All right. So taking a look at the little letter, right? Great work so far on your investigation into what happened when we lost contact with the ACM pod. As our team investigates what kept this pod from docking, your models and arguments will play a key role in helping us understand what could have caused the pod to move away from the space station. Was there a problem with the amount of force exerted by the thrusters? Your explanations will help us interpret the data we are trying to recover from the pod. We hope to have some data soon. Keep up the thorough work. Awesome. So we're going to make 2 models, one for each of these claims. We'll send them to the space agency to explain how the thrusters could have affected the pod's motion. Claim number 1, what we're focused on is the thrusters are the only thing that's responsible for changing the velocity of the space pod. Claim number 2 is that the thrusters and the space station both are responsible for the change in velocity of the pod. So your first model, right, you know what you're showing. And then the second model, I hope that you know what you're showing. The only thing that you do not have here is you do not have the space station, okay? So that's not a force that you're talking about. So hopefully you're going to be able to show both of these models. You can also add in annotations to your models to help explain your thinking. Take your time, complete the models, and then restart the video. Well, restart, so unpause the video. So hopefully you came back, right? And this should be projected while you guys had been doing the modeling. Okay, and I can't wait to check those things out over the weekend. So explaining these forces, now we're going to write about the two claims in terms of cause and effect. So we're looking at the relationship between thruster force and the change in the pod's velocity. This will help us interpret the data. And here, your cause is the force and the effect is the change in the pod's velocity. So understanding a cause and effect relationship can help you infer what led to a particular result. Make sure that you add this key concept into your notebook. You need to make sure that you state that a stronger or weaker thruster force will have a specific effect on the pod's motion. So let's review these examples to help us understand how to explain cause and effect. So remember, instead of using a jar lid, right, what we ended up doing is we used those pass cars to shoot out erasers, right? So the pass car caused the erasers to start moving across the floor, right? What happened when we started using different amounts of that force from the pass cars? So there are two parts to the writing activity because we have two different claims. Make sure that you use from your word bank, okay? And we have the modeling tool diagrams as well. So you have a lot of things that you can choose from, but I really want you to work on writing a really, really, really good cause and effect explanation, right, for this. Lastly, today, right, I would like you to do this self-reflection just to see where you think that you're at. All right, kids. I hope you have a great day, and I will see you guys on Monday.